It's done. I'll just double check. Okay, good morning, everyone. Thank you all for coming. I just wanted to say, before I introduce our opening speaker, I just wanted to say a few remarks of welcome and background about the conference in general. I think the idea for this conference goes back to, I think it's 3 years, when I met George Ellis at a philosophy and cosmology conference in, and I met George Ellis. Ooh. I met George Ellis, is that better? I met George Ellis at a philosophy and cosmology conference in Oxford, which I think was a birthday celebration conference for George, if I remember rightly. And I was sitting next to George at breakfast one day, and Paul Davies was sitting across the table. And George said to Paul, look, if I wanted to meet a philosopher who really believes this block universe nonsense, who should I talk to? And Paul said, he's sitting next to you. And so George and I got into a very enjoyable and somewhat heated discussion about the kind of issues we're going to be talking about at this conference. And at some point I said, we should really have a conference to thresh these things out. And then we started arguing about whether it should be in Cape Town or in Sydney and the rival merits of these two places. But I soon realized I was on the wrong side of that argument, because even if Cape Town wasn't quite as beautiful as Sydney, then there's no doubt it was beautiful, and I'd never been there. So it was very much in my interest that the conference should be in Cape Town and not in Sydney. And so then that idea was just sitting there, and then it became possible to turn it into a reality thanks to the generous support of the John Templeton Foundation. And it's now the opening conference of the grant that we had in Sydney for New Agendas for the Study of Time. So I want to thank the Templeton Foundation for their generous support. And thank George for playing the role of our local host here and for finding us such a magnificent conference venue. At least on the conference venue, I really have to admit defeat. I think I've never been able to organize a conference in Sydney in such a gorgeous setting. Okay, so welcome to everybody. And now I'm very delighted to introduce for our opening talk Carlo Rovelli from Marseille, who will be known to most of you. His name, I think, will be known to all of you. And he's going to be speaking to us on Change Without Time, Contemporary Physics and Time. Welcome, Carlo.
Thank you very much. I'm told that should I use this? I should turn it on. Just keep moving on. One. Okay, thank you very much. It's wonderful being here. It's wonderful being such a group of people, group of minds here. It's a honor for me, but also a burden to open this conference. We have two hours. I'm not going to bore you talking continuously for 2 hours, because otherwise it will be painful. So I was thinking that either I talk for 2 hours in a row, and then for 1 hour, and then we have discussion for 1 hour, or, which I would prefer, perhaps, if you have questions and want to stop me, please do. And then I go slowly. So we turn this into open interchange. I'll only reserve the right to, if it goes too long, to say, well, let me please get to the end, and then get a block of time at the end for discussing. If for you it's okay. So if I am in difficulty with an argument, I'll say, no, it's not this. I am not a philosopher. Many people in this audience are, so I keep my hands ahead about a certain philosophical naiveties, which I will say. I'm a physicist. And so the contribution I'm trying to give is that of a physicist who talks about time in contemporary physics, contemporary meaning the last 100 years. Now, at first sight, the collaboration between physicists and philosophers, it's simply defined and clear, and it has been extraordinarily successful in the centuries in terms of cross-fertilization of the two sort of manners of investigations. And the respective competences are, at first sight, pretty well defined. Right? On the one hand, the philosopher sort of has analytical tools and can have arguments, can analyze clearance of arguments or positions. It can have a priori arguments. It can try to talk about model terms, what is possible, what is necessary. On the other hand, the scientists look, or is supposed to look at nature and see what is contingent, what happens to be, take notice of how nature happens to be. So this is the first look story. Of course, we all know that it's not so easy, and the domain and competence are not so clearly separated, as is shown on the one hand by the bad philosophy or good philosophy that scientists use all the time, and on the other hand by notoriously and embarrassing mistakes that even great minds in philosophy have done. Just think, for instance, at Kant transcendental, therefore a priori reconstruction of derivation, for him, of Newtonian mechanics, of the whole of Newtonian mechanics. The difficulty, it's for many reasons. I think one key one is that the conceptual structure that we use for thinking the world is to an extent which is hard to evaluate, to pinpoint, deriving from our experience, and as such, it has the limitations of our experience. So it's easy to think in terms of ideas and concepts that are strongly rooted in our experience, but our experience can be not good when we enlarge the domain of experience which we're looking at. So let me make a simple example that will be a sort of simple-minded, ideal metaphor for what I'm going to say, which is the following. Imagine there's a philosopher who is interested in space instead of time, and who sort of comes up with the idea that it is intrinsic in the nature of space, and therefore is necessary every time we talk about space, to distinguish the up and the down, the vertical direction. Now, this philosopher may not necessarily be stupid, especially if he lived in Athens, right, in the 5th century, because it's so immediate to our apprehension of space, that space is organized vertically. But then we all learned Newtonian theory in primary school, and we learned that it's much more convenient to think about space as something isotropic. And in fact, more than that, we saw the astronauts, right, floating in space and having a direct perception of isotropic space. So we understand that this up and down property of space, but the notion of up and down, are not necessarily good as grounding a general description of the universe, in spite of the fact that they are so good here for us, for our life, and if George doesn't take it bad, for chemistry, for psychology, for what was it, the mind, and for metaphysics. So what I'm going to try to do is to argue that we are in risk of this kind of mistakes today about time, namely as talking about time in terms which might be shown to be relevant for the world at large, like contemporary physics. And if you share some sort of basic naturalism with lowercase n, because I'm reading your book, so at very minimal level, we think that we want to have a worldview which is not badly in contradiction with what's supposed to be best science is telling us today, then we want to avoid this kind of mistake. So I'm going to play this in a few chapters. The key one will be 4 and 5. This is where I want to get at, and then idea to which I'm attached, which I want to present to you in spite of doubts I have about it. It's a speculative idea, which is the fifth one. But I'll go slowly, I'll build slowly, going through the pieces of physics on which we are confident. They are now 100 years old: special relativity, then general relativity, then quantum theory, by taking various aspects of time and discussing them. And this will also, I think, be useful as an opening talk at the conference for putting on the table a number of things which will be certainly largely discussed in the rest of the conference. And just to close this introduction, let me have a sentence there, to just an arbitrary sentence. I just picked up an arbitrary sentence about time, which I will come back at the end to make concrete what I mean. This seems a completely simple, factual statement about something happening in the universe. Let's say there's a rock there right now, far away in the space between the galaxies. Silent drifts a rock. A slow, continuously undisturbed is flowing time. And at the end of the day, there's nothing controversial in this statement. I'll try to convince you that basically everything in the sentence is meaningless. Not wrong, meaningless. So let me start by chapter number 1, which is the present. And here we're talking about special relativity. And I'll say a few words. I've tried to organize this in a way which is comprehensible for psychologists, for Jeremy, for physicists, for Faye. So I'll probably be non-comprehensible to many people. So at some point I will say, obviously, the things which are totally plain and obvious to some of you, but I hope will be useful for somebody else. Now, special relativity, so it's from 1905 Einstein theory about space and time, right? It's almost unquestioned today. It's virtually unquestioned. I would say unquestioned. Nothing is unquestioned. Teaches us that this is space-time, so this is the event. The event is just a here and now, something happening in a point of space at a moment of time. Teaches us that it has this causal structure. If there's an event here, something happening in one point, the rest of the event are divided between the future, which is whatever happens inside the light cone. These are light rays moving. The past, and then this particular areas here, which are the space like wedge. Okay. Now, what it means physically is that if I know everything about a region, a little bit thick region here in the past, I know everything which is needed, I'll try to say this correctly, to say everything I could say about its causal development, about this region here. Namely, any knowledge of what happens elsewhere is irrelevant as far as predicting what happened here once I know what is there. There's nothing, this causal structure which is time asymmetric, by the way. I mean, the theory is completely, the same is true the other way around. Now, before getting to my point, I want to make a little observation which I hope is useful to some of you, which is the following. This is Minkowski space, the way it's usually drawn, okay? But that's a very bad drawing. This is the way it should be drawn. And a lot of what I say about special relativity follows from that. What do I mean? I mean that we measure this is a distance in meters, and this in seconds, right? So between me and Jeremy there are 5-10 meters, okay? So the thickness of the wedge is a time interval which is of the order of a nanosecond. Nanosecond is very small. Okay? If Jeremy was in New York, the thickness of this wedge would be a millisecond. A millisecond is still much below the threshold of our perception of time. I checked with a psychologist here Saturday night. So as far as our perception is concerned, and as far as microphysics, biology, chemistry, etc., this wedge is a line. In fact, it's a line called present. Okay? It's a set of things happening, taking arbitrary times, smaller than a nanosecond, like everything that matters in chemistry, which is happening contemporary to the event here, simultaneously to the event here. This, of course, since it's an angle, becomes larger and larger when I go far away. The moon is in a second, on Mars in a few minutes, and it becomes very big if I go very far. Right? If I go to Andromeda, it becomes millions of years. Now, why I'm saying that? Because I want to talk about the present, and the present is a set of points which are simultaneous. Now, the main message of point 1 is the following, that if you look in special relativity books, there's something which is called the Ice and Simultaneity Convention, which is a way of saying which point here, which event here is simultaneous to this event here. And main point I want to make is Ice and Simultaneity Convention is a convention. It bears no ontological, physical, no meaning whatsoever besides being a convention, and it's obviously a mistake to take the load, the heavy load which is associated to our non-relativistic notion of present and carry it over to the definition of simultaneity given by Einstein convention. Now, Einstein convention, for those who don't know it, is the following thing. I take an object moving in space-time, an object could be a guy running, or this thing here, and I say that this event here is simultaneous to this event here if sending a light ray which bounces back and comes back, the following happens, that the time interval between emission and A is equal, numerically equal to the time interval between A and reception. Okay? Obviously, this definition is not, this definition of simultaneity is not transitive, right? If A is simultaneous to B, it's relative to this object. So it's, if in B there is another object moving, the definition of simultaneity relative to this other object will not, which include points which are not simultaneous to A. But if I fix A and I fix the object, I have a set of points which is the simultaneity surface. And what I want to insist is that the simultaneity surface means nothing at all as far as trying to understand the world is concerned, and definitely does not carry any of the notation, the connotation of our what we mean by present. But what's the present? Well, present, if you want to extend the non-relativistic notion of present to special relativity, we can try to do things. For instance, we can say the present is whatever comes after the past and before the future, and then the present is a full wedge relative to this point here. Or we can say the present is what I see. I mean, my present now is I see George there, so what I then present is just my past life, right? That's another way, possibility of extending the notion of present. Whatever I do, I don't get a transitive notion of present like there was in non-relativistic physics, which allows me to think in terms of coexistence transitively. Now you say, wait a moment, we read cosmology books, and in cosmology there is a well-defined notion of present, right? Because it's called cosmological time. I mean, we think that there's a Big Bang or something, and this is the Big Bang, and this is the galaxies, the history of galaxies. And suppose there's a clock on each galaxy, and then you can define a time in each galaxy, which is a cosmological time. And you can think, well, right now is what's happening in the universe is there are all the galaxies which have the same cosmological time, namely the same time from the Big Bang. This is nonsense, in my opinion, for two reasons. First of all, it's just as a first step, it's completely unrelated to Einstein simultaneity, right? It's a simple calculation. You take Friedman, what is simultaneous, what is happening in Andromeda according to Einstein simultaneity is not what is happening to Andromeda now according to cosmological time. So let's take cosmological time as the real good definition of the present. This is what happened in the present in the universe now, okay? I think this picture should just make this hypothesis completely becomes irrelevant. Because the previous picture was in the wrong assumption, in the simplified assumption that the universe is homogeneous. But the universe is not homogeneous, and in particular, these are two galaxies that merge. This is two real galaxies that merge. It's a picture of two galaxies that merge. Now, there's no reason whatsoever for which the time of this from the Big Bang is equal to the time of this from the Big Bang. In fact, in general, will not be. So what is this event of these two galaxies mixing? When is it happening? At the time of this galaxy or at the time of this galaxy? Is this time galaxy meeting a galaxy from the future? No. We're clearly stretching. What is this all nonsense? It's trying to take a notion which was meaningful in non-relativistic physics and bring it up to special relativistic physics. It's trying to take a notion of up and down, okay, and trying to be meaningful in the space between the galaxies where there is no up and down. So this, of course, leads us with a problem, or something which we may view as a problem. If we try to give, summarize the Einstein simultaneity, these surfaces here are very bad to give them the non-relativistic meaning of present because they're not transitive, don't agree with cosmological time, which by itself may be of use. and also because they don't make sense in GR, which is more or less what follows from what I said about the galaxy. Now, this is the non-transitivity of one of the definition of present. How to react to that? Well, I think this afternoon there will be a lot of discussions about this problems, various positions. I don't want to take a strong position about that because whatever I say, probably somebody will disagree with. But one solution is what is called block universe, which might mean a lot of different things. Hugh will talk about that in the afternoon, so will be much more precise than me. If one take it in the strongest meaning, namely in the same sense in which in non-relativistic physics, I think the two things in the present exist together. In the same sense, I want to say that everything exists together also in the past and in the future, four-dimensional. Then I think I am overstretching. There's an argument for that, which I know is the one in Putnam, which is based on the fact of saying if A is simultaneous to B, and then B is simultaneous to C, C can be in the past of A, so elements which are in the future of the past one with respect to another one, they both exist together. Okay? I think this argument is wrong because it takes a notion which is not transitive, simultaneity, throws away, forgets the fact that it's not transitive, assumes that it is transitive to try to define an equivalent relation. Okay? It's nonsense. It's exactly the same mistake if I say, I'm in the same room as Jeremy. 10 years ago, I was in the same room as Ted Newman. Therefore, Jeremy is the same room as Ted Newman. No, it's a mistake. What is a mistake? Use transitivity where it doesn't belong.
Can I ask a question?
Sure.
You said we could, you don't mind interruptions, but in what sense can you talk about time flow being non-physical? In what sense could there be time flow at all in the universe?
Good. I think this is going to be discussed at length in the conference by various people, and it's going to be point 5 in my discussion. So if you don't mind, we address this after point 5. What I'm saying here, I'm not defending block universe in its strongest interpretation. However, I'm saying that choosing, well, another possibility, another possibility is to say, wait a moment, the present is a notion needed to understand the world, because it's part of our understanding of the world. Therefore, special relativity misses something. Special relativity just doesn't see it, but there is a present. There's a true present in cosmology or in, okay? In my opinion, this is purely an opinion as a scientist, this is a mistake of the same sort of saying, we of course know that there is a high up and down, okay? Newton equation doesn't see an up and down, therefore something is missing in the Newton equation, I have to add it. Okay? The universe described by Newtonian physics, there's no up and down, but there is a real direction, it's the universe, and I have to add it. And I think that trying to add something to physics, don't look at me like that. I hope I'm not too much in disagreement with you. I hope you have a good answer because if I'm too much in disagreement with you, I think I'm wrong. So, but I mean, you're talking this afternoon. A physicist this morning and a philosopher, Roberto Unger, are writing a book about the need of adding the notion of time to physics, which is sort of missing. I would try a different escape route, which is point 5 in my presentation, which is speculative, which will be the last one, which will not be to think there is something missing fundamentally in the microphysics in special and general relativity. So I do not think that the fact that we don't have a notion of present should force us away from talking about flow of time, about processes, about change, and I will try to argue that in fact, in spite of the fact there's no present, we can still talk about change and so on. Let me make one small remark about that. Of course, if I choose an object, in special relativity and general relativity, this object is represented by a world line. Along this world line, there's a time that I can define. What I'm saying is that there's no global notion of time, which does not mean that time is sort of solipsistic thing attached to each line, because of course any two objects, suppose this is an object, this is another object, okay? This is me and this is George, okay? I have my own time in the sense that there's a time that can be computed along this line, and there's another one, but of course we communicate, right? So with respect to this point here, all this part here of George's story is the past, all this part here is George's story is the future. There's just a nanosecond, which is ill-defined, which is neither past nor future, okay? This is all that, yes?
So when you say time flow, you mean something like a preferred foliation, or here's something kind of...
Absolutely not.
But here it's between, it's sort of a local kind of coordinate.
I'm just saying here that there is a notion, with respect to A, there is a notion of past and future, obviously, also that pertains to the temporality.
But it comes down to a sort of simultaneity relation. So
yeah, but it's ill-defined up to a...
But my point is sometimes people by flow mean something more than they
Absolutely, absolutely. I'm perfectly aware of that. So I'm
you
not
just
talking
mean
about flow in that sense.
You just mean the simultaneity.
For the moment, yes.
Some people might think that was evidence for something
Yes.
even more.
I'll get to the flow in point 5 of the
Okay.
So conclusion of the first point, the first of the 5 points, I think the consistent global notion of present is at odds with today's physics, which seems to be going in the direction that the only meaning of tensor statements is self-referential. And I urge you to if whatever understanding of temporality you have, if it needs a notion of present, either to recognize that it's not a now, it's a here and now, it's a local notion of present, some sort, or to figure out whether it could be consistent with physics as we know it. For consistency, I also mean when it doesn't want to act too much to make a physics. That was point 1. Now, when we get to point 2, point 2 is, allow me to do that, is, which kind of biscuits you prefer. Whether you prefer these or this. So, I'm talking about general relativity. And this Newton speaks and Leibniz talked. I'm talking about general relativity now, so I'm stepping 10 years in the future with respect to special relativity, 1915 Einstein, right? This is still perfectly solid for the psychologist, well-established physics of 100 years ago, almost uncontroversial today. Now, it's well known that Einstein was very emphatic on the fact that general relativity changes dramatically, in fact, takes away the notion of space and time. And just with this, general relativity takes away from space and time the last remnant of physical objectivity. Einstein, 1916. This is what a time interval, the reading of a clock, looks in general relativity. It can be expressed as a certain expression in terms of the gravitational field. So let me give you, this is important also for the physicists who know general relativity very well. Let me give you my account of general relativity in few lines. Oops. Now I understand why there are screws here. So, this is the world for Newton, right? There's a space. In fact, let me actually show it. For Newton, the world is a space. In space, there are particles that move, time flows, and as time flows, particle moves, right? Then somehow, in the 19th century, Faraday and Einstein figured out that there are fields on space. And field, the electric field, is something that fills up space and moves, and is a real thing, right? There's a beautiful paper by Faraday. Faraday lines are real things, this field things. So, and in fact, modern physics is entirely in terms of fields, particle and quantum excitation of fields. So we have fields now. Einstein realizes that beyond the electromagnetic field, there's also gravitational field. Okay, so there's the magnetic field, gravitational field, but also realizes that the core understanding of Einstein that Newtonian space is the gravitational field. So in fact, Newtonian space is not rigid, but it's also a field, which can move very much on the same ground and very much at the same ontological level, status, as the electromagnetic field. So we get to a modern physics is entirely a, in fact, if you read theoretical physics journals, there's all sort of imagination about all sorts of theories, but they are very little imaginative. Almost all of theoretical physics is in terms of a single ontology, which is that of a general covariant quantum field theory. Whether it's expressed in terms of little points like Raphael, or Feynman-like, or quanta of gravity, or whatever, but there's just one entity. Even the string theorists, which are a little bit slower with that, that do most of calculation on a fixed background, then realizing more and more that background is just quantum fields around. And in fact, this is very explicit in recent development of string theory. So the only thing we have is a gravitational field, other fields over it, and that's the ontology of the world according to physics. And what is time? Well, time is just a measure of the number of sort of little steps, a measure of the gravitational field along a certain line over it. And this is the formula that keeps the amount of time passed from here to there. Which means, in terms of the sort of Leibniz-Newton debate, which the debate loses any sense, in my opinion, after generativity. Let me put it this way: when Newton introduced this picture, particle over space and time, he was not at all following the dominant Western tradition, right? He was strongly against the Western tradition, the dominant Western tradition, from Aristotle to Descartes, which is that there's no space. Space is not an entity. For Descartes, space is a property of things. It's the rest extent, it's a property of matter, in a sense, to an extension. And for Aristotle, space is just a relation to matter. No? It's the surroundings, the internal boundary of the surrounding things. So for both, if you take away matter, space that remains. And Newton goes on and on against Descartes to try to show that there is a better way of thinking space, which is to think that space is something very different from matter. He says explicitly, as long as something completely different from matter, space has to be there and it has arguments. The strongest argument is that it works very well. Say that slowly because what matters is time here. What Einstein does, by recognizing that space-time is just a gravitational field, in a sense, is nothing else than going back to pre-Newtonian ontology about space. Okay? The novelties that also true about time. So in a sense, Leibniz, I don't know why everybody thinks about Leibniz when he thinks about relational expositions about space-time. It's Leibniz really in the correspondence with Clarke was arguing very well, argumenting very well, but he was defending a view which was a dominant view in Descartes, in a sense, and from antiquity. That was a unique view, because of course there was Democritus and another tradition from which Newton took, namely space as an entity. So from this point of view, if this is correct, then to say, then who is right between the substantivalist and the relationalist debate? Well, everybody's right and everybody's wrong, right? The substantivalist can say, of course, look, space-time is an entity. Of course it's an entity. Here it is. That's the entity. That's the gravitational field. Okay? So we're right. And the relationalist say, no, wait a moment. The point about substantivalists, as we understood it, is that there is an entity different from the matter, all the existing matter around, on which things moves. So that we were right, because there's nothing else that feels around, and space-time relations are just property of fields. Everybody's right, it's just reduced to a terminological distinction, where you want to call, yes?
Do you regard the topological and differentiable structure of the manifold as a partial exception to this?
No, I would say that they are a phenomena of the gravitational field, like you.
But the way,
So I would agree with you on that.
well, except we're replacing the gravitational field with a different kind of structure. I mean, in the way that mathematics is set up, it doesn't look like that. Perhaps there should be.
I agree, but this will become very much technical. In the way in which mathematics is set up, it doesn't look like that because there's a sort of fixed manifold. But I think that the role of the invariant and the differential is just to erase the manifold and make it physically relevant in a sense. So my picture of the gravitational field, like yours, it is an entity which define, so the manifold comes semi-classical in a sense. The moral of all that is that time is not an entity, it's just a property of an object. The object being the gravitational field. It's counting how many little steps are in the gravitational field in a sense. So every time you think about time, whatever you think, remember this is what physics is telling us. And I think the old relationalist, the substantivalist debate is outdated because of this reason. Now let me go to something new. Let me go to the more new part, and there's a little intermezzo before going to the main point, which is my chapter number 3.
Carlo, could you just go back to that slide?
Okay, so a little intermezzo before getting to the heart matter. Intermezzo about discreteness. Now let me bring in another piece of physics, which is 100 years old, which is quantum mechanics. So again, if time is determined by the gravitational field, there are all sorts of reasons which I'm not going to believe that the gravitational field is a quantum object, because everything which is dynamical is a quantum object. And so this is a quantum quantity. The quantum quantities are characterized very often by being discrete. Okay? The angle at which a particle is deflecting a Stern-Gerlach experiment is discrete, the energy of the harmonic oscillator is discrete, the energy of electromagnetic field of each mode is discrete, and so on and so forth. There are all sorts of indirect arguments, which again I'm not going to review here, which are written all over in books, to indicate that space also is likely to be discrete once you take into account quantum mechanics and general relativity, and time is likely to be discrete. And one expects, somebody questions the actual numbers here, but the majority expectation is that discreteness is of the order of this size here, very small length size, as far as length is concerned, and there's a corresponding time size there. So I believe that pretty uniformly modern physics tend to say that time, whenever you measure time, is something which is discrete. Discrete with the small steps of this order here. Okay? Time again being a property of the gravitational field. Now, why do I want to say that? First of all, because most discussion about time from the philosophers that I hear, this time is assumed to be continuous, but probably is not. But also, this is a parenthesis, right? I am surprised by the fact that the argument for discreteness of time is in the philosophical literature. If you read Hume in the treatise, there are 2 long chapters just to argue that time must be discrete. Okay? That's the second argument he used. This is Hume treatise. In fact, the first argument is much older. It goes back to Democritus and is in Aristotle. And roughly, I'm not going into that. I just want to mention that, but just to remind you, if you know the arguments, roughly the point is that if it is continuous and is a set of points, this is true for any magnitude. Let me say it for time. If time is a sequence of instants, and the instants have a sort of zero magnitude, if there isn't a minimal amount of time, but it can be arbitrarily small, then I have to think it's a set of instants. But then, if time is a set of instants, one instance had no duration, 2 instants have no duration, 3 instants have no duration. As long as I add instants, I never have the duration. So how can I get duration out of instants which don't have durations? Now, these are philosophical a priori argument of the kind that the philosopher discuss. Part of my, just what I'm saying goes into the direction, be careful about those kind of arguments, but I want to say also something in the opposite directions. Are really those arguments so wrong? The common point of view about this argument is they're wrong. Okay? And the usual response to these arguments, which in a sense they all go back to Zeno, so the solution of the Zeno paradox is against continuity. Continuity of space, continuity of time, continuity of matter. So the usual argument against Zeno is, the continuum is well defined. Just study mathematics, study Weierstrass, Cantor, study the limits, study the definition of real numbers, and you'll figure out that infinite series converge, and so on and so forth. And so it's wrong that continuous is defined as seem to be implied by this. Now this might be wrong, but I have doubts about that, and I just want to present your doubts to you. First of all, the fact that it's a continuous solution doesn't really by itself say much about the physical viability of that particular solution for the physical problem. There might be additional input which come from physics which are not considered. And specifically, let me be much more specific. If you look at the mathematics as a continuous, which is rarely done in these discussions, you discover that the continuous is not a set of points, of course, right? A set of points don't make it continuous. For instance, if you want a topology, if you want to make a line, a continuous line, definition of continuity, you need the set of neighborhoods. So what defines a continuous space is not just the points, it's a point plus something else, some structure. So the continuous is made by it's a set of some structure, and it is this structure that determines continuity. So if anything, time is not a set of instants, but it's something else that is on top of the set of instants. Now, I want to push that too far because I'm not a philosopher, I'm not capable of going into that, but I want to say somehow from the point of view of physicists, the intuition that there's something wrong with the continuous, that ancient atomism used for matter, like Leucippus and Democritus to get to the atomic hypothesis, has been so immensely useful for the later development of science, and historians recognize the debt of Newton and Dalton for chemistry and physics to ancient atomism, that discarding a priori the corresponding arguments for continuity of space and time seems to me a bit dangerous, and I would invite philosophers to look into this. I do not know if the question is just one position. Well, the question is empirical and there's nothing to discuss a priori. It might be, but I think nevertheless that the intuition of a continuum is not so natural after all, and should better be analyzed in its components a little bit more. I don't want to say more about that at this point.
Well, it's absolutely clear that it's not empirically testable. There's absolutely no way you can prove there's a continuum anyway.
You can prove that there is a minimal. That was an argument against atomism, but now we know that matter has atomic structure. So how would you?
If I ask for experimental proof there's a continuum, you will not be able to give it.
You said you could disprove the continuum.
Ah, yeah, but you could disprove it.
You may be able to disprove it,
Okay.
but you will never be able to prove it.
Yeah, sure. That's one point against. Yeah, absolutely. Yeah. Okay, so real temporal intervals from quantum gravity are likely to be discrete. I think there might be some open question for philosophy. Let me come to the main point. And I hope. Yeah. Minutes. Other questions so far? Yes.
I was saying that then one may argue that it's more scientific than the discreteness hypothesis, because it can be falsified.
Yeah. Yeah.
If you don't find the right scale, then it must be smaller.
Okay. That's why we physicists should try to be philosophers. Okay. Now we come to the main point of all this, and main message I want to get at on 4.5, which is, I think that if you bring these inputs together, well, if you bring the inputs of general relativity and the inputs of quantum mechanics together, to some extent, we are forced to just throw the notion of time, which doesn't mean the idea of change, the idea of processes, the notion of time, a time that labels somehow instants one after the other one, into the same place where we threw the notion of up and down in fundamental physics. On the one hand, general relativity tells us that space-time, the thing here, well, that was not space-time, that was an electromagnetic field. Space-time was this. The gravitational field, this is the gravitational field, it's a solution of Einstein equations, right? It's the gravitational field in its development in time. It's hard to use words. So this is the gravitational field at some moment, as time goes on, This is a solution of Einstein equation. So classical physics is a solution of Einstein equation, a solution of classical equation of motion. Now quantum mechanics tell us that the solution of classical equation of motion is an approximation. This is only true, it's only valid, only makes sense semi-classically, and it doesn't make sense microscopically, if not as a element of a calculation. I'm referring to, if I have a particle that goes from here, if I have a particle that goes from here to there, in quantum mechanics we can calculate the probability amplitude of going the particle from here to there, from point x and t to point x prime t prime. We may compute it by summing all trajectories, but we are forbidden to think, unless we use some particular views of quantum mechanics, that there is an actual trajectory that it has followed. So the trajectory of the particle, according to standard quantum mechanics textbooks, is only true if we disregard quantum mechanics. We don't want to disregard quantum mechanics, so there's no trajectory of the particle, so there's no space-time. Simple. All sort of indications that time disappears in a fundamental description, quantum mechanical description of gravity. One, which is probably you have seen many times, is that if you just take the equation of general relativity and the equation of quantum theory, bring them together, you write the Miller-DeWitt equation, sort of the Schrödinger equation of the gravitational field, and there's no time variable here. I don't, time is just gone from there. I think you will talk that in much more detail. Now, what does this mean? And I would like, yes?
I just, can you go back to the previous slide?
Want to talk about the Bully Bomb? Want to talk about the Bully Bomb?
No.
Okay.
I just want to, there's a sense in which each of the sentences on top is in a different way unclear to me. And this isn't like an objection. I guess it's a request to phrase them a little more explicitly. In terms of classical general relativity, if we want to say space-time, or time in particular, is just something about the trajectory of the gravitational field, presumably we don't want to put it quite that way, because what we mean by trajectory usually refers to a development against the background of a time. Okay. I take it, you must have something different by the word trajectory in mind there than what we usually mean. And I'd like to know a little bit more about how to think.
In a couple of
usually we think of trajectory, like I say, as some kind of an account of what something is doing as a function of time.
in the next slides, this is a precise answer to it.
A figure against the ground.
Right, that's right. That's
yeah.
right. So there's a question about, this is just a question maybe about English, about how to put that more faithfully.
Yeah, it's vague. I'm aware, and I hope this is half of the question, right?
The second half of the question is about the right side. It's implicit in what you say on the left side that things like fields can have trajectories, not just things like particles. Okay. But if things like fields can have trajectories, then it's not clear what you mean by denying that in quantum mechanics trajectories don't exist. There's a perfectly exact trajectory of the quantum mechanical wave function, for example, or something like that, that is a perfectly explicit and exact account available of the development against the background of a fixed time of something like the quantum mechanical wave function. It's not clear what stands in the way of thinking about that as the trajectory of the physical system that we're describing.
Okay.
So those are just two questions.
Okay, so the left part, I hope will be more clear in the next part. For the moment, let me give a technical answer. By that I mean a solution of the Einstein equations up to all possible ages, including time reprogrammatization. So that cannot be expressed as the development of something in T, because it's up to the possible development.
Right.
Okay? As far as this, yes?
I was just going to say
I'm sure you are more subtle in that. So
the words to use here is that the trajectory is in a configuration space or something of that nature rather than in space itself.
Sure. No, but still, but
thank you.
Discussion then makes good sense as a trajectory configuration space versus some kind of wave packet or something like that.
no, but it's still not. It's still not a motion. It's still not. It's still not a position configuration space as a function of time.
this will be next responses
Right,
about that.
right.
Next two
Good.
responses about
Good.
that. And then,
I
yes.
guess we'll just, would it help to replace the word trajectory by history?
Yeah, absolutely. That's what I should have written if I had been more here. Absolutely. And this, of course, about this part is much more complicated because it, whatever we say has implicit a way of thinking about quantum mechanics, right? Or even interpretation of quantum mechanics.
Right. Right.
So you and I could disagree in the sense
Right.
that
Fair enough. Okay.
okay, you know what
Right.
I mean.
Right.
Okay, so this is the main story of the talk. And I hope you will follow me carefully on that. I hope you're not too tired. I want to do physics. I want to do physics. Times get entangled. So let me take a system, a very simple physical system. The first one we study at school is a pendulum. Okay? A pendulum, what we study at school in Physics 101, is that we can do physics of this system, and the system is described by a variable. So this is a system that is approximately 1 degree of freedom, which I call x. X is the I don't have enough hands. X is the angle with the vertical of this thing here, or if you want, the displacement of the pendulum from its equilibrium position. And doing physics means studying how this changes in time, evolution of time, and being able to make predictions how it goes. So I need time. So I need x and something that tells me time, a clock, okay? And then I'm instructed to write equation of motions, and some equation of motion, or Lagrange, Hamiltonian, something, and to look for all possible solutions. And each solution, the space of all solutions is labeled by A and phi. That's what I would call phase space. It's Lagrange, so the space of histories. And for each one of this solution of the equation of motion, I know how x depends on t. So if I know which solution I am, you give me t, and I can predict where. This is what we learned at school. Now I want to observe that the same physics can be formulated in a slightly different manner, which is the following. I have a system, okay, where I can measure two things. One is this angle, and one is this angle. The angle between the 12th and the position of the handle. Okay. I call these two things partial observables, just to give them a name. And each couple of partial observable, I call it event. There's a space of all events and a space of all possible couples. I write the equation of motion, doesn't matter, and I list the possible solutions of the equation of motion. The possible solution labeled by A and phi, and for each given A and phi, I have the set of the possible couples which are allowed, which allow me to make some prediction about what is possible to see, what is not possible to see. What's the difference to the previous one? I never mentioned time. I never picked up one of these variables as the time variable. So instead of describing physics of this system is the same, right? Instead of describing it as how position evolves in time, I describe it in terms of how two quantities, this angle and this angle, are related to one, could be related to one another. I make a list of possible sets of events that can stay together. Now, why I'm doing that? First of all, I asked, excuse me to the psychologists and maybe some philosophers, but Jeremy is here, so this is applied just for Jeremy. This can be done precisely in a sort of slightly more precise language in mathematical physics in a Hamiltonian framework. So let me, you can sleep for 30 seconds and wake you up when I'm done. So the extended configuration space is a configuration space times R, the space of X and T. The extended phase space is this cotangent bundle. Since it's a cotangent bundle, it has a symplectic 2 form, which is I call omega. The entire physics is given by a function here, a single function here, where this function vanishes is what is called the constraint surface. This geometry is sufficient to determine histories in the constraint surface, which are the integral lines of the vector fields which are annihilated by the 2 form, by the symplectic form, right? And these are the motions. These are exactly the motion. The space of the motion is phase space, which is labeled by A and phi, amplitude and phase. And I want to claim that the same thing can be done in quantum mechanics. I'm not going to do full lectures on that, but this is consistent in quantum mechanics. You have a suitable Hilbert space, suitable objects, and you can compute amplitudes. And amplitudes are what? Are things that give probability, associated amplitudes to couples of extended configuration point, couple of events. So a function of x and t, x prime, t prime, which in terms of usual language are just the probability that system in an eigenstate of x prime go in an eigenstate of x in the time t minus dy. This can be done, yes?
A question about the idea of using, the angle of the clock hand. I mean, it's obviously going to be something periodic. So there's going to be points at which it's occupying the same state, and presumably you'd have to identify them. So
I want to open it up somehow. Otherwise, yeah. Otherwise, it's not going to be equivalent to the normal relativistic one. Correct. So my identification of t with just the angle should be implemented by something that counts on.
Right. Okay. Yeah.
So
the counter as well,
yeah.
showing how many times.
So it goes to 12 and then 13, 14, 15.
Yeah.
It's expensive.
Yeah.
More expensive. It's more expensive.
This may just be a question of words, but that last sentence kind of doesn't fit together. If you don't have a notion of time, you can't have anything predictive, because predicting is something that you do in time.
That's not true. You could predict that the other side of the moon is
Yes.
you could predict that the other side of the moon, up to the point where it can be seen, would be much the same as the side that you have seen.
Okay, this is a complicated question. So this is the case in which I don't know how to answer. Can we discuss it a bit? This is a yes.
But can you say, when you said what the probability, how to pass the probability is, you said it in terms of the ordinary way of thinking, where it's things evolving through time. Can you say what the probabilities of probabilities are in this timeless framework?
Yeah, in this timeless framework is that viewed in another manner. Somehow, imagine that there is a set, not necessarily ordered, of measurements of x and t for this thing without disturbing it. Okay. Then you have a column of x and a column of t that goes together. So you have a set of events. Okay. Now, I'm capable of saying which events might belong to the set and which don't if I just know 2 or 3 of them. So if you give me all your measurements, I look at them and I say, no, that's not achievable. Or this other one could be possible. Or, well, this other one I can only read t but not x, I can predict x. This other one I can only read x but not t, well, I can predict t or some possible t's.
So it sounds like we have a set of events here.
Yeah, set of events, yes. That's
But also just that, the kind of thing you just said also seems like the right answer to the worry about the use of a word like prediction.
Yeah, but
what
George.
you have in mind is
Yeah, but George
inferring-
may have a counter argument to this.
But I take it that the kind of thing you're going to want to say is that what you mean by words like that is just the possibility of inferring a larger pattern from small
That's right.
pieces.
That's right.
And,
But then inferring.
and it doesn't have to do, it doesn't have necessarily to do with any notion of specifically temporal relation.
Absolutely.
between-
That's what I would have answered to
Right.
George. I didn't because I knew he would have had it. Yeah, absolutely. So we can maybe come back again. Because again, this is still 0.5. Huh? But let me. So now people who didn't follow the mathematics can wake up and get to the point of the discussion. The point of discussion is that I want to claim that dynamics, standard Newtonian dynamics, is usually interpreted as a description of evolution of dynamical variable in time, can equally be interpreted as the description of the relative or the possible relations between partial observables. Families of possible relation partial observables, families being labeled by phase space, which is the space of phase space. Okay? Now, you can say, oh, very good, what have you done? I mean, you've lived too much in France, this is an exercice de style, like the French say. I mean, you've just taken something simple and rephrased something complicated. Okay? So why I'm doing that? Because I think that this is possible for any standard dynamical system, but this is necessary when the system includes gravitational relativistic gravity. Why? Let me give you a zero-minded argument for that, which after all to me remains the strongest one. The core of general relativity, for the psychologists who haven't studied general relativity, is the following. If I have two clocks, okay, which are equal and are precise, and I move them one up and down, wait a little bit, and bring them down, and then look at the reading, they read something different. This is a simple-minded interpretation, the first empirical content of general relativity. I mean, general relativity is complicated because Einstein figured this out 100 years before we can actually measure it, but now we can measure it with so this is just take one clock up, another down, bring it down, one is ahead, one is below. General relativity predicts what is the change in the which is not very difficult, it's just time times the difference of gravitational potential divided by c squared, it's a simple calculation. Now, the prediction gives the evolution of the upper clock with respect to the lower clock, which is time. No. The prediction gives the evolution of the lower clock with respect to the upper clock, which is time. Oh, wait. And clearly the theory is treating the two variables exactly on the same graph. The reason one is not that this clock here is more time than this other clock here, obviously. Okay? Is this clock which is a dependent variable with respect to this is an independent variable? No, I mean the theory doesn't say anything about that. It just says that there are two quantities of which I can predict the relation if I know enough of the initial state of the state, the overall history in which these things are. So there isn't a preferred T in the mathematics of relativity. There is a coordinate T, but this disappears from all predictions because of different variance. So here's how you could think in quantum gravity. Think of this as a region of space-time, but except that now this region is not really described by a solution of the Einstein equations because there's no space-time in between. A sort of fluctuating space-time, depending on your better intuition of quantum gravity. There is some summing of all possible Feynman, all possible space-time. So in particular, the summing of all possible times. But if you measure or interact, if the system interacts with something here and here, so around in the boundary, I can construct a state which gives me what is what were the interactions here, and this is what I call a process. It might have the structure of an in part and an out part, and I have an amplitude which gives me the probability from which I can compute the probability of what happens. And in a theory like the theory in which I'm working, loop quantum gravity, just one of the possible attempts to construct a quantum theory of gravity, Raffel, Fay have other attempts. All these quantities are well defined. The Hilbert space of this, this functional amplitude of that. So I talk about processes, and but I never mention time. It's never time. So in general relativistic, now let's do that concretely for general relativity. Space of the event, I can take space of fluid geometries and other fields on a boundary. There's an extended space, there's a Hamiltonian constraint, which now is not a single function. There will be a vector space here, the equation of motion, the boundary state, and there are transition amplitudes, and all these quantities are well defined in the theory. So that's the conclusion of point 4. I think that the notion of time is not needed to do mechanics, and in fact is misleading to try to impose it.
Can we just go back one?
I've been a little bit fast here.
Sorry, let's go back one before. You said that the amplitude of process is the probability of what happens.
Is from the amplitude I can compute probabilities appropriately squaring and normalizing.
Yeah, but what's the probability of?
Okay, because I shortcutted quantum mechanics in the previous.
It's a probability of what happens in outcomes.
Okay. In classical physics, I can have what the theory tells me is which sets of events are compatible with another. So it tells me that some events can stay together and all the others do not. In quantum mechanics, this is not given because we have probabilities. What quantum mechanics gives to me is a probability that set of events happens or not happens.
Yeah, so the word it happens means things are happening. There's a
Yeah.
time.
I think what I'm arguing is that one can talk about happen, one can talk about process, one can talk about change, and so use all this intuition. So you see, the point is that time has all sorts of connotation in our mind. I'm trying to separate one from the other. So when I keep some, and you're saying, look, you're still using it. Yes, I am.
Is your boundary, are your boundaries these correlation events, though? Is that the happenings?
Yeah.
They're not necessarily involving time. Time being defined by the correlations, the events. So the
That's
boundary
right.
events.
So I'm not throwing away all the temporal intuition. I'm saying that one can keep temporal intuition without having a variable, which is the time variable, which is much weaker than.
Are we to think of the final boundary as in some sense of the future and the other one as in the past?
That's
Or do we think of them as symmetrically as two boundaries?
so far everything is symmetric, and what breaks the symmetry is point number 5. Yes. Okay, so that idea that forget time as long as you want to write a description of the world consistent with quantum mechanical generativity, and come to the last one. Because I used the metaphor, the example of the up and down, right? So I think you're all familiar with the fact that in Newtonian theory, just forget up and down. The equation of motion are in a homogeneous space, but then there is up and down. So we need a story that tells us how, in a physics without up and down, we experience an up and down. And in Newtonian physics, we have this story. There's a planet, a big planet, the Earth is pulling gravity, and so it determines the preferred direction. So here is the. You still have energy? I'm talking to. Here's the idea. And this is a speculative idea. It's called the term of time, and it's an attempt to, maybe it's the main idea I want to go, well, second main idea I want to present. I've argued that nothing is special about the time variable when doing dynamics. I've argued that in reality there is nothing special in general. There's no sense in which this angle here is more important than this angle here ontologically somehow. So they're all similar. So therefore, what is special about time? Nothing is special as far as mechanics is considered. Generativity is sort of bringing all variables on the same ground. Once you define for the people, well, technically expert, when I divide by the diffeomorphism, I remains with quantities, none of which is time. And a lot of literature is of the same, well, let's call this is the time. Look, among these variables, this is the real time. G00 is the time. The derivative of G00 is the time. The volume is the time. This thing is the time. Okay? I will say no, none is the time as long as mechanics is concerned. So where do our experience about time passing come from? And it seems to me that we can say that everything that has to do with the phenomenology of time has to do with thermodynamics in one way or the other. It's thermodynamics that determines, I'm not talking about the direction of time. I'm talking about which variable is the time. It's much stronger. Everything which has to do with thermodynamics is ultimately thermodynamical, memory, sense of flowing, etc., 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 breaking of reversibility, and so on and so forth. So this suggests something. The key observation is this. If you have a time variable, then you have a Hamiltonian that evolves in this time variable, and in a thermodynamical setting, in a statistical setting, you have equilibrium states with respect to that flow. But, and Gibson and Boltzmann tell us how to write these states, for instance, the canonical framework in this manner. But if you have that state, you can read out from that state a time flow. You just take the logarithm of rho, you read out essentially h, and then it generates the Hamilton equation of flow. So there is the following: the time flow might be of thermal origin and determined by the statistical state. So let me give you the mathematics and then the physics. This is the mathematics. Yes.
Well, I'm intrigued a little bit. Can you pull back the previous slide? When you say that all features of temporality are thermodynamic, you refer to things like irreversibility.
And memory
and memories, etc. Okay. That might be called thermodynamical in the sense that we consider non-equilibrium thermodynamics, right?
Yeah.
Because in equilibrium thermodynamics,
yeah.
everything, we are just dealing with static states which don't show any evolution whatsoever.
Yeah. So why do we talk about
when you want to start about Gibbs and Boltzmann and that particular equilibrium state, that is just that tiny part of thermodynamics which ignores everything irreversible.
Yeah,
and now you want to start out with that tiny part and reconstruct the flow of time from equilibrium. But surely equilibrium thermodynamics does not imply or has nothing to say about non-equilibrium thermodynamics.
That's right.
Including irreversibility, memory flowing, etc., etc. So
that's right.
It seems like, how are you going to succeed in this project?
It's a main objection to this entire story, the one you just said, to which I have an intuitive answer. I do not have a good answer, a convincing technical answer. The intuitive answer is the following: if I'm able to talk about equilibrium states, then I'm also able to talk about correlations within equilibrium states, which are time dependent. And therefore, essentially, this is a statistic, right? I'm doing statistics on the maths. So I have all the fluctuations around states. This is a sort of chapter one of something that should then tell me what is the second law of thermodynamics and approaching to equilibrium. But it's not technically there yet. So I think this is.
I should still say that fluctuations about equilibrium thermodynamics have to be fairly small fluctuations, and therefore themselves only a small subset of non-equilibrium thermodynamics.
Of course.
You're just going to a slightly larger subset.
Of course.
Still a small subset.
Of course. If you want the intuition, like quantum field theory, like a white one, once you have the vacuum state, you can write any other state.
Yeah.
Okay, but that's half an answer. I believe that's full answer.
This is a question in a slightly different direction, and not a matter of disagreeing with what you say, but I'm not sure why you think there's nothing on the microphysical level in the following sense. Go back to Newtonian mechanics. Okay. Ask on a non-ontological level, on an operational level, okay, and acknowledging that Newtonian mechanics can be reformulated just in terms of these correspondences like you're talking about. Ask on an operational level in Newtonian mechanics what's the difference between space and time. Okay, that is, you have some four-dimensional you have some four-dimensional manifold. It's smeared with mass densities. Okay, and you say what's the difference between space and time there? A lot of people would answer, here's a fundamental difference between space and time there, and this is one that makes sense on a perfectly microscopic level. Make slices through this manifold, okay, three-dimensional slices, yes? It turns out that if you make, that there's one family of slices that has a special property. The mass and momentum distributions on one slice can be inferred from mass and momentum distributions on the other slices. Slices perpendicular to that don't have this property.
Can I interrupt you?
Sure.
I think this is a good answer. In fact, that's why I only talked about that after quantum mechanics and after general relativity. This is a good answer in the setting in which you were talking about. namely a given space-time in which things evolve with respect to...
But even in general relativity, it's going to be the case.
But not, yeah, even in general relativity.
Even in general relativity, it's going to be the case that there are foliations
yes,
of this
but not in quantum gravity. Because in quantum gravity, you don't have a single space-time. You're in a sense fluctuating over all space-time. So the only thing you can talk about is the evolution in the configuration space of the gravitational field. In a sense, histories of configuration space. And there, this doesn't work. So
okay,
as long as we're talking about the physics in a space-time, I agree. But when we talk about the dynamics of space-time,
well, no, but you say even in classical general relativity, where we do talk about the dynamics.
Well, there are two things which are called classical general relativity. Physics in a given space-time.
No, that's not what I mean.
Okay. And,
I mean full, full classical general relativity. Even there, okay, there's going to be, I mean, let's see, right, one has to put it much more carefully.
I know, and
but you're saying there's no descendant, there's no identifiable descendant of the thing I was pointing out about Newtonian space-time and classical general relativity.
I'm saying there are too many, not there's no.
No, but there are some ways of slicing it that still aren't going to be connected by simple rules, where the conditions, there are going to be some ways of slicing things up where things are connected by simple rules, and there are going to be other ways of slicing things up such that on different slices, things aren't connected by simple rules. Really? Okay, we should talk about this.
I think one way of possibly answering the question, or re-asking the question is, in your picture, it looked like you had two space-like boundaries. You didn't allow a time-like boundary. One might ask, why is that? And is that...
Right, good. Yeah, it's hard for me, I should have a crisper way of putting this, and I don't have one offhand, but I'm skeptical of the blanket claim that there's sort of no identifiable descendant, even in a fully dynamical, classical general relativity, of this kind of distinction. And what you're pointing to, right, is getting at the same kind of point. But of course, I should have a crisper way of asking the question. So maybe we can talk about it.
So I think I had a related kind of over here. I wanted to put it more in terms of the way you set things up. I mean, so whatever physics we come up with is going to have to, at least effectively, sort of recapitulate the kind of correlations we get between particles entangled or not. And again, the probability is just a single sort of non-relativistic one particle. But surely the patterns of correlations we so imagining now having a system of particles, I guess some correlated, some uncorrelated. And the system of measurement, we perform a system of measurements. And the statistics we get between a pair of correlated particles. So now I'm thinking of varying x and keeping t fixed in the framework versus the correlations we get for a single particle, keeping x fixed and varying t. They're quite different, right? So
they are different as long as you are in a given xt geometry, in a given geometry, and you look at particles geometry. Because each given geometry has a causal structure which tells us that there's some time-like direction.
So you're imagining in your system I can have a system of kind of I've got my events and so
I'm talking about the dynamics of the field, the gravitational field.
There's sort of ones and zeros. You think I can't look at that pattern of events and kind of pick out some as saying, oh, that's a correlation between a pair of particles. That's a correlation for an evolving particle.
But I'm not talking about particles in a space-time.
No, but that's not his point.
Maybe I didn't.
I mean, tell me if I'm not expanding on it. There's
let me put it this way. People have looked at the phase space of general relativity at length, trying to see maybe in the phase space of general relativity there are directions which are more temporal than the others. People have done that with some success, right? And maybe I can identify something as time there. Okay, fine, good for them. But I think that what they're trying to do is to pick up one. General is being done, pick up one variable and say, look, this is more similar to the pre-relativistic, pre-general relativistic time. So let's extend the notion of time to
But it
this.
depends similar in what respect. I guess here's the question I'm asking, and this is related to the way he was putting it earlier. Go back to the Newtonian case, and then we'll try to crawl our way up to the classical general relativistic case. In the Newtonian case, another way of what I'm saying is, look, there are surfaces in this four-dimensional Newtonian four-dimensional space-time over which these are what we end up calling equal time hypersurfaces. Okay? Over which the laws that we think exist don't impose any specific, correlations among the observables.
There are no things like that in general relativity. There are kind of constraints.
Let's see. I don't see how that could be the case. Once I have a solution, well, let's see that focus.
Once you have a solution,
No. I take it back. Okay, I'll have to think about it. I'm sorry. I keep talking, and the content of what I'm saying keeps being. I should be talking.
So all this discussion, of course, was about point 4, right? So for the sake of point 5, please grant me point 4.
Okay.
Okay. And now, so assume there is no time. Do you see what?
I just wanted to say something to your response.
Yeah.
Again, when I'm sort of saying imagining correlations between particles, I'm not assuming that there are fundamentally particles, but what I am assuming is, we know effectively there are particles, and these measurements, are real measurements that we know exist, and so must be recapitulated in a framework.
Yeah.
So, are we going to go very wrong if we just take those, those very probabilities that we wrote down, some of them being the things we actually empirically now measure as probabilities of correlations between particles?
Fine.
So there's going to be patterns in your quantum gravity probabilities that look like.
Right. So then let me take it just as a. I don't make it too strong a point then. I make a much weaker point. I think that trying to hunt into the general relativistic dynamics a pattern which reminds us of relativistic time might be done. It might be a good game, but I don't think it's a useful game to understand the universe. In my opinion, it's the same game as trying to hunt into the real universe what is the true up and the true down. You can do it, and you can. It's only possible, right? Everywhere in space-time, after all, there is the point where the curvature is zero are few. So there's always a little bit of curvature, so you can always have a little bit of acceleration. So you can say, well, it's a little up, a little down. And maybe the universe, I can define the average of that all over the universe. So the entire universe is sort of up and sort of down. I can do that, but am I doing good physics? I don't think so.
I think the purpose of my question was sort of I can sort of see you want to go to a level where you're not building any of those things into the basic story. I'm kind of interested in where you think it's going to come back. Since we know
That's point 5. I think that where it comes back, it's from a different direction, which I haven't said yet, right? So.
Can I make this a quasi-technical comment that might be useful to some people who are not experts in gravity, which is that you sort of drawn an analogy between phase space of general relativity, what you call the phase space of general relativity, and space-time. So you're trying to, as people say, deparameterize phase space, which is often known as the problem of time. Find time within something that doesn't necessarily have time in it. But if you ask where did that whole framework come from, it came from the canonical way of describing general relativity. Had you used instead a history's formulation from the very beginning, the problem in this form might not have arisen. And in fact, I'll argue that it does not arise in that case. So it may be well that people understand that a lot of this discussion in detail is tied to a canonical, sort of Hamiltonian way of thinking about relativity, which had to do with evolution in time. That's a pre-relativist notion that you pointed out. That could be the origin of mismatch.
In fact, the origin of mismatch is also, it reminds me, since we're in the South Hemisphere, I live in the North Hemisphere. In the Greek literature, there's all this discussion about for the people who are on the other side, the things which are up are down, and the things which are down which are up, which is a self-contradictory statement. Right? Why is it self-contradictory statement? Because one is trying to formulate something in terms of a language which doesn't permit that something. So one is using a conceptual structure, which is the old, trying to use the old conceptual structure to describe something in new conceptual structure. And I'm doing the same thing here. I'm using temporal language for describing something. Now you're saying the history point of view, it's clear. I agree. I completely agree. My definition of phase space, which is space A and phi, the space of histories, is not the phase space that fits the time. And what I'm going to take called state in a moment here, it's going to be a state in phase space.
But that's the space of classical solutions of the Einstein.
Right.
Not the same thing as the space of all histories that one sums over and passes.
Right. Right. So it's not, yeah, this is small.
So, so in some sense, it's
Yeah, yeah.
space
I agree.
initial data, although freed from the
I
reference to a particular slice.
Maybe I should get to the end. I mean, I know some people are tired. Do you want to add something?
I was just going to say that yes, old and new doesn't mean less right and more right necessarily.
Sorry?
Old and new doesn't necessarily mean less right and more right, respectively. It could be that we were studying dynamics for a long time, and then Minkowski came along and said, fuse these things together and have space-time. But then and then he said that space and time individually would be doomed to fade away. But the thing is, it's also been pointed out by a minority since then that maybe this space-time fusion is a historical accident, and that the true history of how one should do science should never have departed from dynamical thinking.
Let me get to the final point, and then I can have a pause and come. So all this discussion was about point 4, right? So is there some mechanical time in the dynamical description of gravity and quantum gravity? And as long as point 5, if you want to understand point 5, give me that for granted for a moment, and let me propose that idea that what we call time is something else. It does not come from the mechanics, and I have to tell you where it comes from. So the technical idea is this. There's an observation here. If I have a time flow, there's an equilibrium. There are equilibrium states, which are sort of invariant in the time flow, but the reverse is true. If I have any state, I can view it as an equilibrium state with respect to a time flow, which is determined by the state itself. And here how it works in the technical part. In the classical part, so this is a classical system, the extended phase space. So this is not the space of the solution equation of motion. This is a state of possible events. The dynamics given by C, so this is a timeless definition of mechanics. Now what is a physical state? Is a state which I can view it defined here, or I can view it defined from the physical phase space down, the space of the orbit of C in its in the surface where it vanishes, into R plus, which is, if I view it defined here, I need it to be compatible with the dynamics. It defines, any state defines a flow through this equation here, which is a more complicated way of writing what I wrote here, given a state that takes its logarithm, let's say I interpret it as Hamiltonian and it evolves in time. Okay? So given any state, it gives me a flow. Now, the beauty of that is that it works in quantum field theory. It works in quantum field theory thanks to this beautiful mathematics, Tomita Takezaki theory, and which actually part of it was developed here in South Africa 10 years ago. There, I'm not going into the detail, but it's also true that a state, a statistical state, which I can view it as a function of the algebra or a trace class operator in the Hilbert space, gives me a flow. And the Tomita theorem constructs this flow, such that the state is invariant under this flow. So what is that? What am I saying? It seems very complicated, but saying something very simple here. Temporality. Let me grant that temporality, all our phenomenology that we relate to temporality, let me grant it that that's thermodynamic knowledge. It's related to thermodynamics. It's always, there's heat, there's memory, there's... But thermodynamics is just statistics. That's how we understand statistics. And statistics is limited knowledge about the system. So you have a system, you have a little system interacting with it. It only interacts with a subclass. It only knows something about the system. Since it knows something about the system, it can say a lot about the system, but not all. And this lack of information creates some special property, some central feature of one particular variable, which is the one with respect to this what you don't know gives an equilibrium state. So in other words, temporality comes from statistics. Statistics come from incomplete knowledge, and knowledge being two interacting systems having not full access to the degrees of freedom of one another. So obviously, we're back to a sort of indexical understanding of time. Right? Time with respect to a system which interacts with a bigger system. So here is the example that I hope could make a little bit more concrete this very abstract. If you take a model, this is a little model, this is done classical. You take an expanding Friedman universe filled with a non-uniform electromagnetic radiation. You declare that this electromagnetic radiation is in the statistical state that describes the CMB, the cosmic microwave background. This is a statistical state. You can write it in a generally covariant manner without ever saying which one is time variable. You use the equation I said, and you compute the time flow. So you compute out which is the time variable. The time variable turned out to be something that labeled in fact, the volume of the units, the Friedman time. So in other words, in a universe field of thermal radiation, where you don't know the details of thermal radiation, you only know the average energy distribution, then the statistical time determined by the state is the one of the expanding, that labels expanding universe. Namely, is what we call time in an expanding universe. This is just a little application of that. So the conclusion of this fifth part is that I say it in the last in the final thing. Perhaps in a general relativistic context, a quantum general relativistic context, we are hunting time. So what's time? Perhaps we are hunting in the wrong position by looking into the mechanics. If we have a mechanical description of the world which is timeless, there's still room, because we have limited access to the microphysics, the thermodynamical description of systems, to have everything which is related to our phenomenology of temporality to come from the thermodynamics, and this being compatible with the usual notion of time in the non-relativistic sense, which works very well for our non-relativistic
Carlo, by using the word epistemic, are you implying that in some sense it's not real?
Well, real can be used as a lot of means. It's not real in the sense in which, no, of course it's real. I mean, heat is real. If I touch something, it's hot. It's real. Heat is very real. It's extremely real. There's nothing as real as heat. Okay. But somehow I can have a description of the world where heat, I never talk about it. And it's a complete description of the world. I only look like molecules that jump around very fast. And in this microscopic description of the world, I never mention heat. And it works very well. And it's not that it doesn't account for it. It accounts for the phenomenon, but the heat is it belongs to an approximate description of what is going on. And it works very well.
Do you mean perspective?
So it's not which is not, time is real, of course it's real. Right? It's just like finish. But what I want to say, it's real in the same sense in which up and down are real. It's real, but it should be understood in terms of something else. More fundamental, which is timeless, and we don't, my sort of tentative message is don't try to bring this approximate notion all the way down to the fundamental physics of the world. It doesn't belong there. Is that an answer? It doesn't mean that you agree. It's just it's a comprehensive answer. Yeah.
Do you have two different notions of relation going on here? Because I mean the volume.
Oh, probably I have 3 or 4 notions.
Yeah. Because I mean you were talking about relational before, and you meant relations between quantities. I can't see what's relational about time in this thermal type.
Because I shortcut it a little bit. If you want to do statistics, it means that you're describing a system in terms of a small number of variables. I think that only makes sense if you have a system interacting with this full number of variables. So in which sense you do statistics? Because a system interacts with another system, it only interacts with, say, pressure and temperature or whatever volume, and so there is an account of what happens here just in terms of the limited number of variables, which is statistical mechanics. So relational, epistemic in that sense also, because it's relational in that sense. A very weak sense.
I think my comment is something like the following. up and down may be derived from something else, but they are very, very rare. You can fall down the stairs, you can't fall upstairs. So however you do it, you must be able to derive a real up and down in this room.
Oh, but the heat is very real. If I burn a piece of paper, it burns for real.
Yeah.
It's just I can give an account of what I think that if I try to understand the microphysics of the world by insisting that there should be heat, the microphysics, I'm wrong. I can just give a molecular account of what happens, and then heat comes from an average quantity. That's only that.
This is maybe to amplify George's question a little bit. Sometimes when people say things are merely epistemic or merely statistical,
I shouldn't use epistemic in philosophy.
I mean, or merely statistical. I mean, one sees this in a lot of talk about entropy, for example, in statistical mechanics. Sometimes people seem to be saying something which really is paradoxical, and I think George was pressing you on whether you were saying something like this, that it's statistical in the sense that if you were to look at the exact microstate of the world, the phenomenon would become invisible somehow. The phenomenon would disappear, okay? So for example, sometimes you hear people say things like, a point in phase space can never be associated with any particular entropy, okay? Or can never be associated with an entropy other than zero, okay? Now, if this were true, this would be really mysterious, okay? That somehow, by knowing more, we make certain perfectly palpable features of the world invisible or disappear or something like that. That had better not be true.
Sure,
okay?
I think we all would agree.
Okay,
Yeah,
good,
absolutely.
good.
100%.
Okay, good.
Yeah,
good.
so don't take epistemic and
Okay.
meaning absolute,
Well,
at all, meaning
that's
more
what's
than a word.
encouraged when you say things like it depends on ignorance. There's some basic sense in which that had better not be true, or else we're just declaring it to be.
It's not the facts of the world that depend on our ignorance. It's the language that we use to describe it as related to an incomplete description. It still burns. It's hot
I mean,
to
what
heat.
you said about heat is perfectly compatible with this.
Okay,
of course
yeah,
we can, of course we
Yeah,
can,
you were
but
good
don't
in it.
need to talk about heat on a fundamental mechanical level.
Right.
But it had damn well better be the case that we can talk about it on a fundamental mechanical level, or else something would be really wrong.
Right, but bringing in.
We don't. It's a
Bringing
fact that we
in
can
more
formulate a complete
stories.
description of the world without using that word. That's true, and that's important.
Yeah. Okay, I'm happy. Yes.
Actually, my comment is directly relevant to that. It might help. I want to defend your use of the word epistemic there. Maxwell, who was one of the founders of quantum mechanics, and thought a lot very deeply about how to think about thermodynamic quantities in terms of statistical mechanics. His view was that, if we're talking about, thermodynamics requires a distinction between transferring energy as heat and transferring energy as work. And on Maxwell's view, that was the distinction between what we keep track of and what we don't keep track of in detail. And that's related to as you were saying, a separation of the many, many variables of the system into, a small number and then all the rest. And that can actually that can be entirely up to us. In that matter of what we are manipulating, what we are keeping track of. That distinction doesn't have to have any deep significance. And when Maxwell talked about the Maxwell demon, where he says, if there were a being that could keep track of everything, concepts of heat and work, that distinction wouldn't even occur to that being. So if you say heat is real, yeah, sure. You put your hand on something hot, you're going to go, ow. Now, is that the hot plate heating you or doing work on you? Well, it's ow either way. The ow is real, the energy transfer is real, but whether it's energy transfer as heat or as work, that can actually be completely an epistemic thing. That can be completely something is relative to a distinction between
No,
here
I
and the rest.
I fully agree. I think that Dave could answer yes, but the microscopic description has the property of being such that the macroscopic descriptions exist. And so this is a microscopic property. Right, that would be your... So
Yeah, no, I
there's
don't
no
think there's deep
contradiction between
disagreement.
this,
Right,
between these things.
right. I don't think there's any deep
Yeah.
disagreement.
Well, I don't want to get into this set of issues, nor into the issues of the reality of A and B series, but I just want to make a very simple point, that your conclusion there that 10 statements, like it is reading...
It doesn't follow.
No, the point is there is absolutely nothing controversial about that statement if we analyze tense from a linguistic point of view. Tense is always analyzed in every linguistic analysis in terms of the relationship between the time of event and the time of utterance. It is always relational, and it is always, and tense is therefore part of one of the language systems of space and time, which are called deictic, because they have to do with pointing. So this is derived from the Greek term deixis, and tense is as much speaker or utterance time relative as spatial deictics like here and there. So, there is just no problem at all.
I'm very happy with that. I'm not sure that all my colleagues would be happy with that.
The notion of present in those terms.
I'm not sure everyone knows what A series and B series.
Oh, sorry, maybe.
Well, I didn't want to get into that. There are some other interesting things, but that kind of anticipates what I will say tomorrow, that there are some, just like in English we only have here and there, but there are some languages in which you have a more complex spatial deictic system, like in Spanish and Portuguese, here, there, and over there, and even in some languages four deictics. But there are also languages which have more, we just have then in English, basically, there's a lexical temporal diathesis, but there are other languages which have more, and which are to do with, then, more than, or something like that,
No, I would fully agree. The A series and the B series, Raphael, is the B series is everything you can say about time in terms of earlier than and later than. The A series is something more about it, which is everything you can say by time in which you say now, the future, the past, the present, the future, the past. So in which you talk about present, not with respect to something, but just present. Probably shortcutting it a little bit. Jerry.
Well, this is again a different topic, but it goes back to Yossi's question. Could you say more about your statistical state of the universe calculation relating the thermal state of the cosmic vector?
Yeah.
And the specific flow about that being the FRW cosmic time. How does that relate to Yossi's reversible? The worry is that the construction uses equilibrium and therefore is likely to lead to a time reversal invariant results, and yet you are describing here cosmological expansion, which clearly has one direction.
In cosmology, you have a change in equilibrium. It's basically equilibrium with a slowly changing time.
Right. Yes, so maybe that's going to.
I need to. I need to think about that, because there seem to be two notions of equilibrium.
Yeah.
Sort of. Yeah.
Maybe what George says underpins how your statistical state of the universe. Calculation of consistency of your framework
addresses that question. Yeah,
it's basically the particle collision time is incredibly faster than the expansion time.
So there is a state, a state in the sort of history sense. which is in equilibrium in the sense which I'm saying,
Yeah.
but it's also has direction. I need to think more carefully.
A question, does it have a direction or could it be equally well expanding or attracting?
It has a direction in that case, yeah.
Yeah.
Definitely, yeah.
Well, I had a more general question, and one of the things I think what I would request is that it seems to me there are so many technical notions in advanced physical theories which are all called time, and that should probably be distinguished in careful reflection. And especially when we are trying to give answers to the question like time is blah blah blah, or time is. I mean, if we are talking about different notions, then we might get ourselves confused if we don't try to distinguish those notions more carefully. And so, in particular, in space-time theories, we have notion of time which can merely be a coordinate or parameter of a certain foliation. And we have proper time, which is calculated on a particular world line or trajectory. And those two have to be distinguished. And
Yeah.
in dynamical theories, we have a parameter of evolution, which we usually call time.
Right.
Just a parameter in the evolution, in group of evolution operator, generated by the Hamiltonian. And then on the other hand, we might have something which is a dynamical variable, which is just a particular quantity or observable of physical systems.
I agree. This
But
is
what I understood you doing in your previous point was to replace a preferred dynamical parameter of evolution by a dynamical system, a clock. And so, if you said you wanted to
can I answer
that
because
phase,
I'm short on time, which
Okay.
I claim it doesn't exist, but.
Well, my question is, in your previous case, I thought you were replacing the parameter by a dynamical variable time and creating an expanded space with an expanded Hamiltonian, and then try to treat all those dynamical variables at a bar. And in that sense, you were saying this is the dynamics without time.
Yes.
In your last point, I think you seem to be taking the completely opposite
That's right.
view, in which you start out with a Hamiltonian
That's right.
or state Hamiltonian,
That's
and then you create another temporal variable,
That's right.
a parameter,
That's right.
which is not a dynamical
That's right.
variable.
That's exactly what I'm
Therefore,
doing. That's exactly what I'm doing. So let me answer. First of all, I couldn't agree more that we use time in a different, in a number of different manners, and all my effort is trying to use as entire pieces of one for the other. So what I'm saying is that when we use general relativity, as long as dynamical phenomena, microphysics is concerned, I don't see the need of trying to single out one particular variable as a time variable. Okay? So all the variables are on equal ground of the microphysics. Worse than that, I think that if one tries to do that, one sort of creates confusion to oneself. It's not fruitful, and there's an impediment to write the microphysics. Having said so, in some context, in some certain context, even after equilibrium in some sense, should be that the variable that we usually call time should have some particular properties. I say the idea here is that these properties are not visible at the microscopic level, if not in the sense that they are saying, but are thermodynamical. That property of this kind are averaged property of the kind of the thermodynamical one, and I'm giving an explicit way. So the formulas, given a statistical state, so given a self-imposed lack of knowledge because we only measure some, with respect to the evolution of a limited number of variables, there is one particular variable that has the same properties as what we call time, and in fact, if we compute it in a specific case, it turns out to be time. Let me. I have a few minutes left, so let me conclude, and then if there are a few remaining minutes, I take more questions. So this was my last point, right? The temporal aspect of reality, I would suggest, should be looked at, not trying to dig into the phase space of generativity or doing funny things with quantum gravity, but just looking somewhere else. So do the microphysics without using the notion of time and relate the phenomenology of time to thermodynamical things. So now you say why this sentence was so wrong, right? Right now, far away doesn't make any sense. There's no far away, there's no right now on Andromeda, there are millions years, which are now, it's just... the fact that the time flows undisturbed is obviously wrong, even in the most possible way. If you have a clock there, the rock goes by, the clock changes with respect to another clock, which is sends message to another clock, it gets all disturbed by that. So time is certainly not undisturbed by, and in fact, it's just a property of the gravitational field which is there and is not something that flows undisturbed. Continuous is not true because it's probably discrete, right? And even worse, the idea that time is flowing by itself is probably the wrong way of thinking. So the entire sentence doesn't make any sense. So this is my summary. My last transparency, there are 5 points which I went through. First, just to remind you, I argued that the notion of present is just bad, in special relativity already and in general relativity especially. I reminded you that whatever you think of time, general relativity teaches us that time is just a property of a field, of something real in the universe, and not a background with respect to which the universe evolved. My third point was to sort of remind you that quantum gravity strongly indicates that time intervals, so this property of the field, are likely to be discrete. My main points were 4 or 5, that's the main message. 4 regards to the microphysics, and I want to argue that the useful way, again, not necessary way, but the useful way to think about the microphysics is to stop thinking about time and talk about the relation between the events, the measurable quantities, if you want. And there is a scheme in which this can be done. At least, frankly, we don't know if quantum gravity is the right theory of the world, of course, or we don't know if other formulation of quantum gravity is the right theory of the world, but in principle it can be done, up to all sorts of technical problems, of course. And the 5th point is that the idea that what is characteristic about flowing of time is thermodynamical, the very idea of flowing, that there is a second law of thermodynamics, etc., and hence due to limited knowledge. So this is the point. The mechanical notion of time is not relevant in the general relativistic context, but there's a different notion, thermal time. This is given by the statistical state, which I think captured everything which has to do with our usual way of thinking time. Even if you don't believe this suggested idea, I think the main message is that if you're interested in what is time in the real world, distrust your intuition, which comes from a limited piece of reality. And that's the end of the talk. Sorry, so long.
Okay, thank you very much, Carlo. We have, in fact, got, I think, 5 or 6 minutes of whatever this stuff is we're talking about.
Since there were no questions, is anybody?
So we do have time for 1 or 2 more brief questions if anyone has one. Nick?
So, to go back to, I'm still trying to understand, I mean, it's sort of today, but to understand the time not being in the mechanical picture. So what about the signature of the metric? I mean, is that going to be a thermodynamical phenomenon? I mean, like sort of -1.
No. I'm taking generativity as it is.
Because that seems to be a distinction in space.
What is the distinction?
Well, that one of the dimensions kind of gets a -1 in the metric. In other words, we get a sign 1.
What are the dimensions of what?
Of space-time.
There's no space-time, because space-time is the same classical quantity in quantum gravity. And once you bring...
We're going to have an effective theory, so is that distinction coming from the mechanics of your theory, or is it
Well, in effective theory, you can start talking about geometry, space-time, proper times, among geodesics.
So there's a distinction there, right? In that effective theory, is it going to come from thermodynamics
Sure.
or from mechanics?
Sure. In fact, I mean, there are a number of works that recent in the direction of trying to figure out this total time, whether it has physical teeth or not, which are exactly in this direction. So where are the cases where thermal time agrees in a semi-classical context with the time, with the proper time?
So the answer is yes.
So
that minus, the differences.
Then they should agree, yes.
It should come from
Exactly.
Exactly.
Yes. I thought you were saying the fundamental theory. Yeah, no, sure.
Wait, I'm not sure I understood the answer to this question.
The answer to this question is, because I might not listen to the question. The answer to this, what he's saying is that in the metric there is a minus and a plus.
Right,
So once you
right.
have space-time and you have a metric on the space-time, there is something you can say about time there,
Right.
different from space.
Right.
And my answer is yes, it's true. This is true as soon as you have a semi-classical state, because there's no space-time metric. And once you have a semi-classical state, you're not anymore in the fundamental theory, you're in the semi-classical state, and then you have to see whether the semi-classical notion of time agrees or not, or in which condition it agrees or not with the term of time. And that's will pose problem. And the answer is yes under some conditions on the state. In other words, this notion of time, we are not talking about fundamental microphysics, we are talking about approximations, and we think those...
But let me ask it this way.
Can I take this question and then...
Okay, sure.
Yeah.
This is my question. I really want to understand. So if we substitute, as it were, change for time, then am I right in understanding that in the thermodynamical approach to and theory of change that you are advocating, irreversibility is actually real? Because usually, when we think about mechanical notions of change, reversibility is actually built in. Am I right in that understanding?
Yes, you understand exactly. Absolutely. So reversibility comes in with this total time, the one that makes it. So, Dave.
This is just follow up to Nick's question. Look, maybe the way to put the question a little more forcefully is this. In every solution to classical general relativity shares this feature of the local signature of the metric. Okay, that the metric is locally Lorentzian. If we're thinking of the transition to quantum mechanics in a simple-minded way as just allowing arbitrary superpositions of classical solutions, okay, then you're going to preserve this feature. Since it's a feature of every classical solution, that there is this characteristic locally Lorentzian signature, that there is this characteristic distinction between space and time. Since that's true of every classical solution, it'll be true of every superposition of classical solutions.
No, I wouldn't agree with that.
Oh, okay, so tell me where I'm good. So where am I going wrong there?
Imagine you have generativity plus two particles somewhere, and four particles interacting in 2 points, two space-time points.
Right.
Okay, then I have two superpositions in which point A and point B are space-like with respect to one another, to one metric, and point A and point B are time-like with respect to the metric, and I can superpose it. And since location is only determined...
That's true, but that's a global rather than a local feature. I mean, maybe this is irrelevant. I'm just trying to get straight on what's going on. In every solution to classical general relativity, locally we have it's locally Lorentzian. Okay, we can change coordinates such that at any point we have a locally Lorentzian situation with the characteristic signature of the metric.
Don't talk about points, talk about where particle A is, for example.
Right. And in that way we can distinguish on a straightforward microscopic mathematical level between the spatial coordinates and and the temporal coordinate. The only puzzle was if we think simple-mindedly about the quantum mechanical case as just arbitrary superpositions of available classical solutions, then it seems like all superpositions will have that feature too. I mean, maybe there's an error in this reasoning somewhere. I'm just.
And we will run them privately too, because I think it's.
Sure.
I'm afraid we're out of time. Or it's time we were out of this joint in order to have lunch. We don't have to be very far out of this joint. Lunch is just next door. But we now have, I think it's a 1.5 hour break. Is that right, Rob? I've got a brief announcement to make. But first of all, let's thank Carlo for a wonderful talk and discussion. The brief announcement is that we're going to adopt an idea which some of you will know from conferences at Perimeter in Canada. On Friday afternoon, we have basically an afternoon for general discussion. We're going to organize some of you into panels, but it'll be very informal. One of the things I do at Perimeter, as some of you will know, is to encourage people at meetings to provide some input into those panel discussions by writing questions on post-it notes and sticking them on the wall during the conference. So I've got a pad here of post-it notes. They're actually restoring, they're actually advertising some drug called Zoxidon, which apparently restores function. I'm not sure what function. But it's made by a company called Pharmacodynamics. So, I mean, in some sense, it's obviously appropriate to this meeting. So I'm going to leave this on the little table by the projector there. And so I want to encourage you to write little questions on, perhaps if we stick them on the wall by the door over here, then we'll have a nice basis for the discussion on Friday afternoons. Okay, thanks very much. Now we have lunch.
Are we able to read out there?
He's very much he's very smart. Right.
Yes. Yes, whether or not we're going to stop this recording. Thank you.